Good morning to everybody. Welcome to the mass transfer course, and today will be lecture 4. So we will study 6 chapters in mass transfer 1. The first one was introduction and motivation. We have covered this introduction and motivation in last 3 lectures. Here we addressed mainly 4 questions. First one was, what is mass transfer or separation process? Now we know that it is a technique to separate the molecules or products from their mixture as per market demand. The second question we address, that is, why should I study the mass transfer course? Here we addressed 5 sectors which are essential sectors of our society, and we have taken number of examples where we find that without separation process these sectors cannot run. Thereafter we address another question, that is, what are the different types of mass transfers? We saw there are mainly 2. One is molecular diffusion and another is convective mass transfer. Then last question we addressed, that is the how will you develop the different separation processes. And here we saw that generally in mass transfer process 2 phases are in direct contact, and there are 3 phases: solid, liquid and gas, and with their combination we can make 9 separation processes. Okay, now today we will start the second chapter, that is molecular diffusion. Already we know that molecular diffusion means transport of molecules from higher concentration to lower concentration in a stagnant media. It is very important. Here medium is stagnant, occurs by mechanism is called molecular diffusion, and the difference in concentration is called the concentration driving force in mass transfer. In any spontaneous process, mass will flow from higher concentration to lower concentration. These 2 things already we know. Before in-depth study of this molecular diffusion, let us be familiar with some basic terminologies. The first one is concentration. Already you know the different kinds of concentration, but we will make a summary of the different types of concentration so that you can deal with whatever you need. Second thing we will address, that is the average velocity. Average velocity. Already you have studied the average velocity in fluid dynamics, that is V bar equal to Q volumetric flow rate by A, cross sectional area. There are some more velocities are also there that we will study, And third thing we will address, that is the flux. Flux, this term is also familiar to you in heat transfer, because you have studied the heat flux, that is joule per meter square second. Joule per second, that is watt per meter square. So flux and heat transfer, why this is very important? Flux is important because if your flux is high, then you can make more heat transfer in small heat transfer equipment. If your heat flux is low, then you will get the low heat transfer with bigger equipment. That's why if you see in your heat transfer course, your first job was to calculate the heat flux. Why you have calculated? Because you want that heat flux should be high. Your objective should be, I can make the heat flux as possible, then I can make more heat transfer in small equipment. Similarly, in mass transfer also, there will be mass transfer flux will be there, and this is very important parameter, because if mass transfer flux this is high, then I can make better separation and in a small equipment. So first we have to, any mass transfer problem, first we have to calculate the mass transfer flux. What way? You have already calculated the heat flux in case of heat transfer, because always your objective was you should keep the heat flux as high as possible. Okay, so these three things today we will address. Now concentration. So concentration of a species in a solution is generally expressed in terms of one of the following. First one is mass concentration, rho I. Please note the nomenclature. We will keep this nomenclature throughout our mass transfer study. Rho I is the mass concentration of the ith species. Okay, that is mass of ith species per unit volume of the solution. And what will be this unit? That kg per meter cube in SI unit. Okay, this is rho I. Rho, what is rho? This is total mass concentration. Total mass concentration of all the species in solution. It is also expressed in kg per meter cube. Okay, this is the concentration. The total mass concentration rho is nothing but the density of the solution. Okay, what is the density of the solution? And that is the total mass concentration. So this is one is mass concentration for ith species, and mass concentration, total mass concentration is rho. And another concentration we generally sometimes we deal, that is mass fraction. Mass fraction is rho I by rho. Okay, so what is this? Mass fraction of the species I in the solution. Now if it is this is the mass fraction, then summation of this mass fraction, this should be 1, isn't it? And similarly summation of rho I will be the rho. Okay, mass concentration of ith species, and if you sum, if there are 3 components, so rho 1, rho 2, rho 3, that will be rho. In this case W1, W2, W plus W3, that will be 1. And there is another concentration we generally deal with in mass transfer, that is molar concentration. That is important. Generally we will deal with this molar concentration, that is Ci. So molar Ci is molar concentration of the species I in a solution, and unit is kilomole per meter cube. kilomole per meter. Okay. And similar to rho, that C is total molar concentration of the solution, that is kilomole per meter cube. Now similar to summation of rho I equal to rho, similarly summation of Ci, that will be the C. Okay. And as there was weight fraction, there will be the mole fraction Xi. Xi equal to Ci by C. C is total concentration. Okay. And Xi is the mole fraction of the species I in a solution. What way we did, summation of Wi equal to 1 and summation of Xi will be 1. Okay. But keep it in Xi, deal with the liquid phase. Okay. But in a gas mixture, the concentration of the species generally expressed in terms of partial pressure Pi. Okay. And corresponding mole fraction will be Yi, that is Pi by P, where P is the total pressure. So we are giving the nomenclature Xi is the mole fraction of ith species in solution liquid, and Yi is in the gas mixture, that is the mole fraction in the gas mixture. Already you know everything, just I am summarizing the things. There are mainly mass concentration, weight fraction, mass or mass fraction, molar concentration, more kilomole per meter cube, then mole fraction, and in case of liquid, the mole fraction we are giving the nomenclature as Xi, and in case of gas, this is the Yi. This is very simple. Now average velocity. So what will be different types of average velocities? Already I told you know that in fluid mechanics you have studied one average velocity V bar equal to Q by A. Q is the volumetric flow rate by A is the cross sectional area. So then that is meter per second. Actually this is the volume average velocity V bar. Okay, first one. Apart from the volume average velocity, there are two other average velocities, that is mass average velocity, okay, that we are denoting as a small u, and molar average velocity, that is capital U. Okay. So volume average velocity already we have studied in fluid dynamics, that is V bar. Okay, this we know. Apart from this, we are introducing two more average velocities. Okay, this is mass average velocity, and that is small u, and molar average velocity, that is capital U. But here you should note the nomenclature carefully, because throughout our study we will use this nomenclature. Now volume average velocity V bar equal to, I told already, Q by A. Okay. Now let's take for three component system, if that is Q1 corresponding that component on volumetric flow rate is Q1, and corresponding two component, that Q2, and corresponding component 3 equal to Q3. So Q1 plus Q2 Q3 equal to total Q. Okay. Now what is Q? That is U1, the velocity, into that cross section. Okay, A. But whatever the mole fraction, that will be the Q1. Okay. Generally Q equal to U1 into A. Okay. But there are three components are moving, so each component has its contribution. So accordingly you have to add Y1 for the component 1, Y2 for component 2, and Y3 for component 3 for their contribution. Okay, where Y1 plus Y2 plus Y3 will be 1. That's mean V bar equal to Y1 U1 plus Y2 U2 plus Y3 U3. U1, U2, U3 are the statistical mean velocity of component 1, U1, U2 is component 2 and U3 is component 3. Now mass, what is mass average velocity small u? For 3 component system U, mass average U, this is the velocity for component 1 corresponding that density, okay, rho 1, okay, and that is rho 2, okay, U2 corresponding rho 2 velocity, and component U3, this is the velocity for the component 3 and corresponding mass concentration rho 3 divided by rho 1 plus rho 2 plus rho 3, okay. So this is very much similar your average grade of your class. Let's take you have a 40 students, so 10 got 10 points, 15 got 9 points, and another 15 you got 8 points. So what will be your average CGPA? That will be 10 number got 10 into 10 plus 15 number 15 into 9, 15 number of student got 9 plus 15 into 8, 15 number got 8 divided by total number of students 10 plus 15 plus 50. Here also similar. What is the average velocity? Okay, average mass average velocity. So this is the U1 is the velocity for component 1 corresponding that mass concentration. U2 is the velocity of component 2 corresponding to mass concentration and or density, and U3 is the velocity of component 2 divided by rho 1, rho 2, rho 2. So that what is the velocity unit meter per second? Here also the unit will be same. Now what is rho 1 plus rho 2 plus rho 3? Okay, so that is the total concentration, that is total mass concentration rho. So this is the mass average velocity. So when mass average velocity, so we are multiplying with the mass concentration with corresponding velocity, that is rho 1 U1 plus rho 2 U2 plus rho 3 U2 divided by total concentration. So this is for the 3 component system. Now if there is a n component system, okay, then mass average velocity will be summation of I1 to n rho I ui plus summation of I1 to n rho I. Now this is, what is this again? This is nothing but your total concentration, total mass concentration, that will be 1 by rho into summation of n I1 to n rho I ui. Okay. So where ui is the linear velocity of the ith species in the concerned direction, the quantity of u does not mean the instantaneous velocity. It is not instantaneous velocity of the molecule. It is rather the statistical mean velocities of the molecules of the components I in the given direction. So ui is a statistical mean velocity. Okay, so this is the mass average velocity. Then what will be the molar average velocity? You understand? This is the U, capital U, molar. So in here it will be the molar concentration, CO1 U1 plus C2 U2 plus C3 U3 plus divided by C1 plus C2 plus C3. So U again C1 plus C2 plus C3 will be total total molar concentration, and this will be your molar average velocity. And for nth component, that will be summation I1 to n Ci ui plus summation of I1 to n Ci. So again this is the total total 1 by C summation of Ci ui. Okay, so we have studied the three average velocities. One is volume average velocity, mass average velocity, and molar average velocity. Now the third thing was flux. In heat transfer you have studied the heat flux. Okay, joule per meter square second. Okay, energy per unit area per second. Okay, or rate per second. Okay, similarly in mass transfer there are two types of fluxes. One is mass flux. Mass flux is kg per meter square per second. In case of heat transfer it was joule per meter square second. Okay, then joule per second you studied the watt per meter square, actually joule per meter square second. So in this case that was energy transfer, in this case mass transfer, so mass flux will be kg per meter square second. Okay, and molar flux then will be kilomole per meter square second. Okay, so in mass transfer there are two type of fluxes, that is mass flux, that is kg per meter square second, and molar flux, and that is kilomole per meter square second. And this flux is important because we know if flux is higher we will get the better separation in small equipment. Always we have a objective to keep the flux high. That was the objective in your heat transfer. Heat transfer also always your objective was to keep the heat flux high. Here in this case we will keep our mass flux or molar flux as high as possible. Okay, now how many, there are different type of fluxes with respect to frame of reference. Let's take in case A, this is the ui. Let's take component y which has component I which has a velocity ui. Okay, now if that is the when I am the observer is stationary. So let's take I am an observer, I am standing and I can see the velocity of component I, then it will move. Yeah, okay, ui is the velocity. I have a measurement, I can measure this. Now let's take I am moving with the mass average velocity, means observer is moving with the mass average velocity. Okay, now if I am moving with the mass average velocity small u, okay, then what velocity I will observe? I will observe this velocity ui minus u. And reference 3 see when observer is moving with the molar average velocity. So if I sit on the molar average velocity and if I measure the velocity of component I, then I will see the velocity of the component I will be ui minus capital ui. Let's try to understand with one simple example. frame of reference. Let's take the example of trains. So there are, there are three types of trains. One is a local train. Okay, so local train has a velocity, average velocity 50 km per hour. Okay, then express train has a velocity 80 km per hour, and we know we have a special train Rajdhani Express. Rajdhani Express, let's take, Rajdhani Express has a velocity at 120 km per hour. So there are three trains. One is a local train, okay, 50 km per hour. One is express train, that is 80 km per hour, and Rajdhani is the velocity of 120 km per hour. Now I am an observer, so I am standing in stationary. Stationary means where I am moving with the velocity of earth, all are moving. Okay, so if I stand in a stationary phase, and if I have a velocity measuring instrument device is there with me, so when Rajdhani is passing to me, I am beside the train track, so I will measure, okay, this velocity is 120 km per hour. Okay. Then express train will come, then it has a velocity 80 km per hour. That is stationary. I am in a stationary. Observer is in a stationary. Then I will see one local train is passing. I am in a stationary phase. Observer is, I am in stationary. Then it is 50 km per hour. Okay. So here UI is the Rajdhani Express, and small u, that is mass average velocity, that is your express train, and capital U, molar average velocity, that is your local. Now let's take, so I am measure these speed of three trains when I am in a stationary observer. Okay, I am standing beside the track and I am measuring three trains are passing, what are the velocity. Now let's take, I am sitting on the express train. When I am sitting in express train, that means I am moving at 80 km per hour. And let's take two parallel tracks are there, and then two trains are going parallelly in the same direction. So I am moving at 80 km speed, then in one track, in other track, when Rajdhani is passing the express train, then if I measure the velocity of the Rajdhani, then it will be 120 minus 80 means 40 km, because the stationary, the observer is moving with the express train velocity. Because if we see, that is, you know, the instant standard knowledge, when two trains are passing, one train is crossing another in the same direction, the relative velocity will be higher velocity minus lower velocity. So in this case, although Rajdhani has a u velocity, but when observer is with the mass average velocity, then that relative velocity that will be ui minus u. Then if I am sitting in a local train and two trains are moving in a same direction, and first I am going in a local train, so with 50 kilometer, then when Rajdhani is passing this train in the same direction, then the relative velocity of Rajdhani will be 120 minus 50, 60 kilometer per hour. 70 kilometer per hour, sorry. So here u that is molar average velocity, when observer is moving with the molar average velocity u, then the relative velocity that will be ui minus u, that is will be the effective velocity with this. So there are three type of velocity where observer is sitting. Frame of reference. So if observer is stationary, then the velocity will be of component I will be ui. When observer is moving with the mass average velocity, then the velocity will be ui minus u, and when observer with the molar average velocity, then u minus capital ui. So this will be the velocity. Okay. So accordingly, the fluxes will be there. Now what are the fluxes? So mass flux, okay, this, then there will be three types according to frame of reference. Relative to observer, stationary observer, when observer is stationary, then mass flux small ni equal to rho I into ui. What is mass flux? Kg per meter square second. Okay. Now see what is the unit here. Rho I means kg per meter cube and u equal to meter per second. So kg per meter square second, unit is matching. So what is the velocity? Okay, if you multiply with the mass concentration or density, then it will be your mass flux. So relative to a stationary observer, that will be small I. We are giving the nomenclature small I. Okay, mass flux small I, that is rho I ui. Relative to an observer moving with the mass average velocity, then small I into rho I, and what will be the velocity? Velocity will be ui minus u. Okay, because if you see here ui minus u. Okay, so that same thing will be here. When relative to an observer moving with the molar average velocity, that is small ji, the flux of ith component. Okay, when observer is moving with the molar average velocity, that will be rho I into small ui minus capital U. So there are three types of mass flux according to frame of reference. Small ni, small I, small ji. Small ni is stationary observer, small I, that is the observer moving with the mass average velocity, and small ji when observer is moving with the molar average velocity. But all are small. Small ni, small I, and small ji. This is for mass flux. Similarly, for molar flux what will be unit? Kilomole per meter square second. Okay. So in this case, the relative to an observer will be capital Ni. In this case, we are keeping all these are small n. Here we are keeping all these are capital. Small n, small I, small j. In this case, capital N, capital I, capital J. Small n I, what will be this? In here what is rho I ui in this case? In this case, that will be rho I. It will be, in this case, it will be Ci into ui. Okay. Now I will be Ci minus ui minus u. Similar to this. Only the change in case of rho, there will be the Ci molar concentration, and relative to an observer molar Ji, that will be Ci into ui minus capital. So we have two types of fluxes, that is mass flux, that is kg per meter square second, and another is molar flux, that is kilomole per meter square second. Again, according to frame of reference, so frame of reference will be three types. One is observer is stationary, observer is moving with the mass average velocity, observer is moving with the molar average velocity. Accordingly, for mass flux, there are three fluxes. One is small ni, that denote what nomenclature we are from, that is all are small, small ni, small ii, small j for ith component. Okay, and in case of molar flux, that is capital Ni, capital ii, capital J. In general, in mass transfer, mass flux, these are not generally used much, but if you have some problem, if you see they are expressing the problem in mass flux, you have to deal with it. That's why you should know this. Okay, generally we will make all the things with the molar flux, that is these are the small ni, small ii, capital Ni, capital I, and capital J. Okay, so here we have studied mainly what are the different type of concentrations. We have seen that mass concentration, then weight fraction, then molar concentration, mole fraction. For liquid phase, we express the mole fraction as xi. For gas phase, we have expressed the mole fraction as yi. That is our nomenclature. Then velocities, there are three types of velocities. One is volume average velocity, one is mass average velocity, and another is molar average velocity. Fluxes, mainly two types, one is mass flux and another is molar flux. Again, mass flux will be three types according to frame of reference, and these are small ni, small ii, small ji, and in case of molar flux, that will be capital Ni, capital ii, and capital Ji. Okay. So let's take one problem for calculation of average velocities. This is worked out example problem from Vikarto 2.1. A gas mixture. What is gas mixture? N2 5%, H2 15%, ammonia 76%, and argon 4%. Flows through a pipe 25.4 millimeter in diameter at a 4.0 bar total pressure. If the velocities of the respective components are 0.03 meter per second, 0.035 meter per second, 0.035 meter per second, 3 meter per second, and 0.02 meter per second, calculate the mass transfer, molar average, and volume average velocities of the mixture. So you have a gas mixture of three component: nitrogen, hydrogen and ammonia and argon, and individual velocities are mentioned here. Then you have to calculate mass average velocity, molar average velocities and volume average velocity. So there are four components. So here we are nomenclature is nitrogen 1, hydrogen 2 and ammonia 3 and argon 4. Now I'll come later. First let's calculate the molar average velocity U, and here it is told that volume average velocity equal to molar average. That I will come later. First calculate the molar average velocity. U will be what is the 1 by C summation Ci Ui, and in this case there are four components and four velocities. So 1 by C equal to small c1 u1, c1 u1, c2 u2, c3 u3, c4 u4. Now this is the concentration of component 1 and this is the total concentration. So this by this, that will be your mole fraction y1. This by this equal to y1. So y1 u1, similarly this by this will be y2 u2 plus c3 by colon, that's y3 this. Okay. Now that fraction is, it has told, so y is the mole fraction of the component ith in the gas mixture. So u will be y1, what is 0.05, 5%, 0.05, velocity is 3, okay, plus that 2 is 15%, 0.15, velocity is 0.035, okay. For third, that is ammonia, that is 76%, 0.076 into 0.03 plus this is argon 4%, 0.04 into 0.02, that is the 0.02, that is, then if you make this, that answer is 0.0303 meter per second. That is your molar average. And here it is mentioned that volume average velocity equal to molar average velocity. It will be generally, that's why now people actually volume average velocity equal to molar, because you see that is coming what is y1 u1 plus y2 u2 plus y3 u3. Okay, although this is the basic definition, but after simplification it is coming. Now if you see that volume average velocity expression, let's see this one. So same thing, y1 u1, y2 u2, y3, we also deal with this. So that's why molar average velocity will be your volume average velocity. Okay, same calculation will come. Now mass average velocity. Okay, what is mass average velocity? Small u, this is equal to 1 by rho summation of rho I ui, and in this case there are four components, that mass average value u equal to 1 by rho. Rho is total mass concentration, rho 1 u1, rho 2 u2, rho 3 u3 plus rho 4 u4. Okay, but these are the gases. Okay, now if you see what is rho 1, rho I equal to pi by RT into m, isn't it? Rho is mass per volume. We know this one. Now what will be total? That will be rho into P by RT into M. Okay. Do you know how it is coming, this thing? Okay, let's see. You know PV equal to nRT, that is gas law, isn't it? Now what is N? This is number of moles, that is what is W weight by molecular weight. Isn't it? Now W by V, that is your rho I, W by V. So W by V, this is equal to that will be Pi. Okay, so W by rho, okay, W by rho, that will be that rho I equal to Pi, actually this is Pi equal to NiRT, okay, Pi V equal to number of moles of ith component RT, this is the, so this will be Wi by N, okay, Wi equal to, then Wi equal to rho I, this is the Pi by RT into M, isn't it? So this way it is coming, and if you take the total, then that will be P total N total, then it will be total pressure, okay, P M by. Now if you make this, because you have a rho I 1 by rho 2, so rho I by rho equal to, if you see, if you make this, then Yi into Mi by M. Mi is the molecular weight of the ith component, M is the total average molecular weight of the mixture. Rho I is the mass density of ith component, rho is the total mass density of the mixture, and Mi is the molecular weight of the component I, and M is the average molecular weight of the mixture. So we have to calculate now M, I know, okay, M1, M2, because I know that nitrogen, whatever components, we know the molecular weight of this thing. And what will be average molecular weight? That is mole fraction into one component 1 corresponding this molecular Y2 M2, Y3 MT, and this is a mole fraction, and in this case what was M1 was nitrogen was a 28, and Y2, and this is hydrogen, and Y3, this is ammonia, this is 17, and this is argon 40. So this is our average molecular weight M. So U equal to 1 by M summation of Yi, what is this, Yi Mi, because this by this, okay, into Ui, okay, because rho by rho I equal to Yi Mi by M. So M will come, then Yi Mi and U is there, okay. So this is the, so then you put this thing, that 0.05, 28 and 0.03 is the velocity for your nitrogen. For hydrogen 15%, 0.015, 2 is the molecular weight, and this is the velocity. For ammonia 76%, 0.076, 17, and 0.03, and then for argon, and this is the average molecular weight, and this is coming 0.029 meter per second. Okay. So you see mass average velocity is 0.029 meter per second, and molar average or volume average of 0.030. So there is slight difference is there, okay. So let us stop today. Thank you for your attention. Bye.